and everything is moving fine. Do you all have your calculators with you? You'll be helping me to calculate, and I don't want the video to be too long because we'll be taking too long in calculations. So, do you all have your calculators? LGK, do you have your calculator with you? Students? Make sure you have your calculator with you, your pen and your paper as well, where you're going to be doing the questions that I'll then give you to try. Okay. Lahakwa, do you have your calculator with you there? Hello, can you hear me? Lahakwa? Lahakwa, can you hear me? Okay. This is, look at this paper. Let me just text this guy. All right, so here's the first one. We are doing May, June 2025. We're doing paper 4-1. This is the very first one. May, June 2025. So we do May, June 2025. Remember that for March, when we do, I also want us to do multiple choice papers because they are very tricky as well. So we need to move fast and we can do all those as well. For March, there is only paper 4-2. But then when you go to May, June, okay? For May, June, you have 4-1, 4-2, 4-3. And then October, November, you have 4-1, 4-2, 4-3. Have you seen this? Are you ready? Anita, are you ready? Can you hear me? Can you hear me? Wow, this is great. So here's the first question. It says a person is using a magnetic window cleaner, blah 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 blah. So it's not about window cleaner, okay? Here's the diagram: magnets. Here are the bar magnets, and here are your magnetic field lines. So what we do know is that our magnetic field lines come from north and go to south. So you must prove that you know that. They come from north and go to south. So this is just what we know. They come out of north and they go into south. This is what happens with magnetic field lines that are coming from a bar magnet. All right. So here, glass is not a magnetic material. Now here the question now says to you, can you state the difference between a magnet and a magnetic material? So this is the very first question they give you. State the difference between a magnet and a magnetic material. So remember when we talked about magnetic materials, we said that for magnetic materials, they are always attracted to a magnet. Always. But if it is a magnet itself, two magnets can repel or attract. Magnetic material, as a simple definition, is any material that is always attracted to a magnet. So we have a magnet, then we have a magnetic material, then we have a non-magnetic material. Non-magnetic materials are not even attracted, they are not even repelled by magnets. Nothing happens. They are not attracted to magnets, they are not repelled by magnets. A magnet can be attracted to another magnet or can be repelled from another magnet. But a magnetic material will always be attracted to a magnet. That's the only thing you gotta say, and you're done. So state the difference between magnetic materials and non-magnetic. Oh, this is easy. You just say magnetic materials are always attracted to magnets. Magnetic materials are always attracted to magnets. Non-magnetic materials are not attracted to magnets. Suggest a suitable material for the magnets in the window cleaner. So now we are going to the second thing. What is a suitable material for the magnets that you are seeing here? So these are bar magnets. And bar magnets are not electromagnets. If they were electromagnets, we would have made them out of iron. Okay? In other words, we would have made them temporary magnets if they had electricity, which made them magnets. But these are magnets that will always be magnets. They're permanent. So because of that, you need to use an alloy of iron, which you can use to make these magnets called steel. So you can come here and say, suggest a suitable material. You can say steel is a suitable material for the magnets. Here they say, explain your answer. As it makes permanent magnets. Permanent magnets or bar magnets. Okay. Label the poles of the magnets in 6.2. Wow. We've labeled them already, so we are fine. North, south, north, south. So that's not a problem. Here they now say, state how the field lines show different strengths of the magnetic field between the magnets. That's the last one now. How is it that the field lines here show the different strengths? Okay. You can say the regions where the field lines are closer to each other are the regions where the magnetic field is strongest. Magnetic field lines, when they come close, then the magnetic field is gonna be strong. So say that and get your mark. Don't leave it out. Once they talk about strength of a magnetic field, it is depending on how close the field lines are to each other. The closer the field lines, the stronger the field. Easy. That's just how it works. So if they are talking about strength of a field, they are talking about how close the lines are to each other. Simple, simple, very, very simple question here. Whatever number this was number 6. Very simple, number 6. Let's come here. All right, so this comes from theory of electricity. When you do theory of electricity, there are things that you must kind of know. Number one, we can say the definitions of important quantities. I'm going to be giving you as we answer questions. Then you must know graphs. 3 graphs. Okay, we call them IV graphs, where current here, voltage here. You should know 3 IV graphs. The first IV graph you must know is for an ohmic conductor. If they give you in full, sometimes they can give you half or they can give you in full. If they can give you in full, it'll be like this. This is the graph of an ohmic conductor. Are you all saying? It's just a straight graph. This is for an ohmic conductor. Or if you want to say an ohmic resistor, here what you have is something which follows Ohm's law. If it follows Ohm's law, then this is what the graph will be. We'll call it an ohmic conductor or an ohmic resistor, which is just like this. It follows Ohm's law, where this is going to be the current I, then this is the voltage or the potential difference. Then the second graph you must know is for a bulb, or we say a filament lamp, which is just your lamp like this. A lamp is a resistor anyway. So here we are just dealing with resistors, but this type of resistor, the graph is like this. It comes in, then curves up, then passes through the origin, then curves again. So this is your ohmic conductor. No, why am I lying? This is your lamp, filament lamp. Okay, I should make sure I label nicely because I can confuse someone. Ohmic conductor is this one, which follows Ohm's law. Okay, this one follows Ohm's law. We call it the ohmic conductor or the ohmic resistor. So don't be shocked when you see ohmic resistor or ohmic conductor. It's the same thing. Then you have the filament lamp, which is just your lamp. Then you have here, which we call the diode. This is now the third graph that you must know. You only have to know 3. Okay? Now here we say a diode. The graph of a diode, or sometimes you see them say a let me put it in full, semiconductor diode. This is the graph. So draw them somewhere. The 3 graphs that you must know. Put them somewhere safe on this 4th of July. Put these graphs somewhere safe. I need all of you to know them. You should know the filament lamp graph. You should know the ohmic conductor. And you should know the semiconductor diode. Do you have them? Put these 3. Did you put it? These are the 3 important ones. Now, here they'll say, name the component. Semiconductor diode. Can you see this? This is the semiconductor diode if you write it in full. Now, the next question which they can ask you is, can you tell us, this is the next question which they can ask you, can you tell us how did you identify that that was the graph of a semiconductor diode. So basically, if it is an ohmic resistor, resistance is constant. Resistance is constant. If resistance never changes, that means your current and your voltage are proportional to each other. They are related because the resistance is constant. Now here, resistance increases as the lamp heats up. So that's why you see it going up. The resistance is the graph, okay? You get the gradient. It's getting steeper. Then it will begin to flatten up. So resistance was increasing when it was becoming steeper. For your semiconductor diode, the easiest way for you to see that it's a diode, here is the easiest way for you to see. There is no negative current. You see, current is the y-axis. So if I want to know values for current, I'm looking at the y-axis because it's the current. You can see they labeled it to say current. Now, for a diode, it's just a component that makes sure that current only flows in one direction. So, remember these three graphs that your examiners want you to know. Here for your diode, remember that current only flows in one direction. So there is no current in the reverse direction. That is a simple answer you can use if they ask you how you saw. So, how did you see? You can see current only. In other words, it doesn't go below here. It doesn't go below 0. You don't find anything here. Only for the diode. Here you can see for our ohmic resistor, we had it here, or ohmic conductor. Here for our filament lamp, we had current in the opposite direction. But we don't have current in the opposite direction for a diode. So you say current only flows in one direction. Through a diode. So this is how you show. You cannot reverse the current. It will not flow. As long as it's a diode, then it will make sure that that current does not flow. Are we together, students? Anesu, are we together? Okay, good, Thema. Anesu, are we together? Good. Draw the circuit. A diode looks like this. You draw like this, then it puts a triangle, which in computer science would have said a NOT gate. Then it puts, wait. Then you put a line in front of it like this. Then you make it continue to the output. So it will only allow current to go this way. If current comes to come this way, it will block. There we go. So this theory, we are fine. What did you know? The three graphs. This is what you are learning in this question. The three graphs that examiners will expect you to recognize or sketch or explain. If we are explaining a filament lamp graph, you should say the resistance will increase as the lamp heats up. Okay? It has curves, and because the resistance increases. For an ohmic resistor or a fixed resistor, this is a fixed resistor or ohmic resistor. What is it? Resistance is constant. So the shape is a straight line through the origin because the current is proportional to voltage here. Because resistance is the same. For a filament lamp, resistance increases. Resistance increases for this guy. Resistance, okay, for this guy, you should say resistance increases as the bulb heats up. For here you should say resistance stays constant. Anyone with a question on this? Dear students, is there anyone with a question on this? Now, we come to calculations. When we do calculations, we should always remember that series, parallel, they have their own differences. But there is one thing that remains undefeated. That is, it's going to be Ohm's law. So, if you are good at electricity, if you are good at circuits, it means you understand how to use Ohm's law, because you are going to use it so many times. This V is IR, because they will always in a circuit give you two things on this formula, and you have to find the third one using the formula. V is IR. For series, there's some information that will help you. This is the information we give you. Say, hey, if you're in series, you must remember that current is the same. You must remember that, okay? If you have two resistors that are in series, remember that current is the same. For parallel, remember that voltage is the same. When we say voltage is the same, what do we mean, Mr. Clarify? We mean that every resistor in that circuit has the same voltage as the source. For current, we mean all the resistors have the same current as the source. So current is the same throughout the whole circuit. So it means from the source to all the resistors, we don't want to see any current changing value. It's the same as the source. For parallel, voltage is the same throughout the whole circuit, which means all resistors, hello, voltage is the same throughout the whole circuit. This is what it means. It means all the resistors should have the same voltage as the source, because it's the same throughout the whole thing. So here, once you see that you have a parallel connection, look at this parallel connection. They are joined on both sides, these things. Huh? They are joining on both sides. Once you see this parallel connection, you know without being told that this is at 230 volts and this is also at 230 volts. The same as the source, because voltage has to be the same in parallel. We cannot break any rule. So now we have voltage. Okay, now S1 is closed, blah, blah, blah. So you have this. And S2 is open. The reading on the ammeter is 3.9. S2 is open. If S2 is open, it means here there is nothing. This switch is open. So current will never come because it can't pass. So there is nothing. That means our circuit is this one with S1 closed. This is our circuit. And we've been told that the reading on the ammeter is 3.9 amps. You are already given Ohm's law. I told you you are going to use this so many times. Look, you have V, the voltage, you have I. So you know they're going to ask you for the resistor is A. Calculate the resistance of A. V is IR. It's so depressing because it's just Ohm's law many times. So how can you not use it? You're going to be using Ohm's law many times. I know that you're going to be using some information from here. That current is the same throughout the circuit. Voltage is the same. The total resistance is good and like this. I know that. But at the end of the day, you have to use this formula for all your calculations. You are going to see what I'm saying. At the end of the day, students, you will now have two things. After doing your shenanigans, your calculations, you will now have two things, V and I, or V and R, or R and I, and you'll be looking for the third one. You will keep using this formula. Become best friends with Ohm's law. You will use it every single time in calculations. So here we write, okay, V is IR. What is our V? We know it's 230 volts. So here you say, you can make R, since they want resistance, you can make it the subject, okay? Ooh, give me a second. You can make R the subject by taking I to the other side. V, it becomes V over I is equal to R. What is our voltage? 230 volts. So you're going to say 230 volts over the current. What is I? 3.9 amps over 3.9 amps. This is equal to R. Aki, what's the answer here? If you say 230 divided by 3.9. Aki, what's the answer? Aki? 58.97 ohms, which you can round off to 59 ohms. So 59 ohms, that's your resistance. You must know the units. Right. We move on. So we have 59 ohms for this first one. I'll be calculating with you guys all the time, okay? I just want you to stay active. Now, since this is no longer a second question, this is now about energy and whatever, let me give you the other formulas we're going to use. The formulas, we have Ohm's law. Then we have the formula for energy. Electrical energy, it is equal to VIT. We are in chapter 4. Any calculation is easy because you must just make sure you remember the formula. If you remember the formula, then the calculation is easy. You just pick a formula which works for that situation. We have work done is equal to the charge QV times voltage. Then you're going to have power is equal to VI. Then you have power is equal to I squared R, but this is power loss. We talked about it. Power loss. That's why we hate current. Because current contributes to power loss. That's why we do transmission at high voltages, so that we run away from current. So if we come here, calculate energy, you know the formula for electrical energy. We are in electricity right now. You know that energy is VIT, which is going to be V you have, okay, I you have, so it's 230 volts by 3.9 amps. Now we need to use T. Now for T, they've tried to trick you because they think you don't know that time can never be in minutes. Minutes are never, there is no situation where we use minutes as the unit of time. No. We use seconds. So it'll be by 5.0 times 60, and it's now seconds. Okay. You just multiply by 60 once to turn it to seconds. Now you have it. So can somebody punch exactly like this? Ignore the units. Put 230 in brackets, 3.9, and then this in brackets, and tell me what answer you're going to get. Letty, what answer do you get if you punch this part 3 the exact same way I've written it down? We are just using the formula for electrical energy, so everybody should know it. Energy in electricity, then this is Ohm's law. Letty, what is the answer here? Letty, are you there? Letty, are you there? Ooh. Someone help. Kelly, what is the answer here? What is it? Well done. This is the correct answer, 100 joules. You can write it like this, okay? For those who want to like converting things to kilo, you remove the last 3 digits, so it becomes 200. You say E is equal to 269. Then you put the comma, 0.1 kilo joules. After you put joules, then you can now convert. So you can write 269.1 kilojoules. You can write it like that. Or you can write 269,100 joules. If you're not sure, never lose an answer never lose a mark for not converting properly. Right. Now they're saying S1 remains closed and S2 is now closed. Basically, they are now just saying you have a complete circuit now. The whole thing. Anyway, we already know this is at 230 volts because they're in parallel. Voltage is the same in parallel, so we put the things we already know. Voltage is the same in parallel. Now, we have been told that we have 3.9 amps here on this. Right, now, let me tell you a secret, everybody. Always look for the word identical. If you have more than one gadget, always look for the word identical. Because identical will be telling you that you have the same resistance. So it makes the calculations a little bit easier. So if these are identical lamps, they have the same resistance. Now, we have found the resistance of the first to be 59 or 58.97. So we know that this one also, the R is 58.97. We may not know the current, but we know the resistance. Why would we say we don't? They're identical. We know that the resistance for this one is 58.97. So it's the same for this other one because they're identical. There we go. It's for A, it's 58.97. So for B, it is also 59.7 because they're identical. So well done, you now know R. Students, tell me, if we have V now and we have R, what do we use? What do we use now that we have two things, V and R? What do we use again? Tell me in seconds. What is it that we keep using? Hello? My students, are you letting me down? What is it that we keep using now that we have V and R? Who is the best friend of all circuits? What is the thing that people don't use correctly on circuits? Why people hate circuits? What is it that they don't use correctly? Hope. What is it? Hope. What should we use now? We know V, we know R. What should we use now, Hope? Hope, can you hear me? Tobo, can you hear me? Tobo, can you hear me? Kevin, Xavier, can you hear me? We use Ohm's law. Ohm's law is the best friend of circuits. So you have V, you have R, you expect them to ask you for I. So you come here, determine the reading on the ammeter. That's current, that's I. Are we surprised? No! We are experienced. We are ready. This is where everything takes us back to. So come on now, V is IR. You say to me, again? Yes, it's a circuit. So what do you want to use? You use the rules, but after using the rules, you come back here. You had two things. You had V and R. Students, don't let me down now. So here you say V over R. This gives us I. What is the V? 200 and whatever. 230 volts. What is the R? 58.97. So 230 volts divided by 58.97 ohms. What is the I now? Students, what is the I? What is the I? What is the I here? If we can say I2, this is I1. What is our I? You get back to the same answer here. 3.9 amps is equal to your I. Well done. So now you have found the current that is going through B. IB is also 3.9 amps. Why do they have the same current? Why do they have it split? We know that, hello, listen, don't let me down. Voltage is the same in parallel, which means current is shared in parallel. I told you, my students, that in physics, there is a special word for this point where you have three or more wires coming together. It's called a node. A node is a place where three or more things, wires or cables, come together. Now, at a node, current shares itself out. So some will come here, which is called IA, and some will come down, which we'll call IB. Because it's a node, it came as one current here, but it will share itself. And then at the second node, the currents will combine again now and form the same value that was here. They will form it again here at the second node. So this ammeter is getting after they combine again. Now, what we know is when it split, we got IA and they told us it was 3.9 amps. So it's 3.9 amps. Then IB, we calculated, we got 3.9 amps again. So we can now say that the total current, because that's the one they want, after it recombines, it is going to be equal to 3.9 amps plus 3.9 amps, which is going to be students, what is the answer? 7.8. 7.8 amps. This is the reading on the ammeter when the currents rejoin. What made us crack this question was the statement identical. So they're identical, which means they have the same resistance, which means when the current is shared, IA and IB will be the same. It will share itself equally, fairly, because the two things have the same resistance. Thank you. Here is the third question for this major paper. Identify components A and B. We know that we have slip rings and we have brushes. So A would be brushes because it's not rings. B would have to be slip rings. Here, C is made of soft iron. Yes. Once you have, look at this. This here outside is your coil. And here is a magnet. So do we have the magnet? I'm highlighting the magnet in green. Here we have the magnet. So do we have the magnet? Yes. Do we have the coil? Yes, in blue. So what is this in purple? It is made out of iron. What is it, this thing in purple? It is there to make the magnetic field strong, to link your field, to make it stronger. So what they said, describe the effect of this component on the generator. C is made up of iron, okay, which is magnetized. Temporarily, which means it's a soft magnetic material. It helps or it strengthens the magnetic field of the magnet. It strengthens the magnetic field of the magnet. That's the only reason we would put something inside our coil, or else would never do that. Explain the advantages of transmitting electricity at high voltages. I feel like we talked about this somewhere. But, oh, here the graph. We talked about the graph. And I told you about the most important thing. The most important thing is the positioning of your coil. Okay? The positioning of your coil. You should know the biggest question that you should ask is, when is induced EMF maximum and when is induced EMF zero? When you're looking at a diagram, when do you get the max and when do you get zero? We hate it when the fields have nothing to cut, if I can say that. If the field is going through, then we will hate it. There will be zero EMF induced. So if your coil is like this, and your field is just going through it, then EMF induced is zero. But if the field is like this, north, south, then the coil, instead of it being open like this, where the lines go in and out, it would now lie in the field. So the field is like this, like this. Your coil now lies in there. Look, it's lying. And the field is cutting both sides. Look at it. The field is cutting, or the coil is cutting the field. Then that is where you have maximum induced EMF. The field loves to cut the wires. The wires should slip in the field, so they cut the field. Let's say that. Then you have maximum induced EMF. So the coil is in the position shown at time zero, which is, what position is this? It's like this. It's lying in the field nicely. You can see your field lines will cut the coil nicely like this. So this coil is making your induced EMF start at a maximum. That's the best situation right now. The best situation is because the field is cutting the line, so we have max. So we are starting at max. We are starting at max. Now, let's go through. Now, here they said 2 complete revolutions per second. 1 second, we needed to get to here and to here again. Otherwise, it's not a revolution. In other words, it gets back where it started. That's a revolution. So it should do it here and should do it here again. So that means it goes down. Let me see if it goes down like this. So it goes down and cuts here. Then it must curve at 0.5. Go back up. Okay. Here's the graph. But of course, you should make it neat. Don't make it ugly like this. The most important thing that my students should know is that the coil should sleep in the field. The field should not go through the coil. If that happens, where the field is going through an empty coil like this, then what we will have is zero. It starts here. Zero induced EMF. EMF induced, zero. All right. That means there's the magnet which is saying north, and there's the magnet which is saying south. Nothing is induced. Anyway, explain that we're now at transformers now. We're done with this. We're now at transformers. Why would we want to transmit at high voltages? We know the guy we hate. We know the guy that is in the loss for power loss, in the formula for power loss. It's current. He's the one. Current is the enemy of progress. It causes power loss. So, what are we going to have? Explain the advantages of transmitting at high voltage. We know that if we increase the voltage, we would have reduced the current. So, we'll have less current, which means less power loss. So, high voltage leads to low current, which leads to less power loss. Less power loss. Okay. And also cheaper cables or thinner cables being used as the current is low. You can use cheaper, thinner cables because you have low current. So why do we do high voltage? For low current, which will allow us to have less power loss and cheaper cables. Then here, transformer calculations. This is the last. If they ask number of turns of voltage of a transformer, I said you should have the three things. Power is VI. This is the power in a transformer. Then we know that power at primary is equal to the power at secondary side. Because we are dealing with an ideal transformer at IGCSE, there will be no power loss. So it means voltage at primary times current at primary, okay? VP IP will be equal to VS IS. Then the last one, VP, voltage in primary over voltage in secondary, is equal to the number of turns in primary over the number of turns in secondary, and vice versa. So you just pick one, you answer, you move on. Here they're saying, what do you have? Voltage. What do you have? Turns. What do you have? Voltage again. What do you want? Turns. Right. Transformer steps up voltage to this, which means this is the outputs after being stepped up. So we have number of turns and we have voltage. So you're going to say Vs over Vp is equal to Ns over Np. Now, since you're looking for Ns, you take Np to the other side. Vs over Vp times Np, number of turns in primary, is equal to Ns. Now, what is the voltage at the secondary, which means the output voltage is 300,000 volts. Divided by voltage at the primary, 25,000 volts. Times the number of turns, 450 turns. This would give us Ns. You're just substituting. Then you get your answer. Right. Who's going to give me the answer here? Thema. Oh, this one is for Tapelo. Tapelo, what's the answer here? Say 300,000 divided by 25,000, then say times 450. What do you get, Mr. Taps? Tapelo? Tapelo, what's the answer? Tapelo, are you in class? Tima, can you help us? 300,000 divided by 25,000 times 450. Tima, what's the answer? 300,000 divided by 25,000 times 450. $5,400 turns. You just used this because that's what you had. You had voltages and number of turns, so you just used this formula. 4,500 turns. Remember, you can write it like this, where it's Vs over Vp, Ns over Np, or you can write it as Vp over Vs, Np over Ns. You can flip it, it's still fine. Okay, I'm pretty happy with this. Now, of course, I'm going to continue this through the night, so I'll dismiss you guys. But let me do chemistry first. Let me mark the register and then do chemistry. I want to give you questions related to these things we have done. Related to this, the transformer calculations and whatever. We're going paper by paper. So I've started. We keep going. Everybody, this is how we revise. So we have May, June 2025, paper 4.1. Now we're going to do paper 4.2 for May, June 2025 as well, and paper 4.3. And our focus is chapter 4, which is electricity and magnetism. Everything to do with those things. We want to answer it together. Are we together? Everything to do with chapter 4. So we need to do everything to do with chapter 4 and make sure everybody's on the same page. We still have to do more questions on circuits. We still have to do more questions on transformer calculations. We still have to do more questions on whatever. That is what I need from you guys. We have to be doing questions all the time, but we are doing topic by topic. And in 2 months' time, we'll be doing full papers. So that's how I'm going to be doing with you. Topic by topic question papers. All right.